The universe is a vast and mysterious place, full of wonders that we are only beginning to understand. Among the most fascinating and elusive of these cosmic mysteries are neutrinos. These tiny subatomic particles are often called ghost particles because they are incredibly difficult to detect. Neutrinos are like cosmic phantoms, passing through our planet and our bodies by the trillions each second, leaving barely a trace. Neutrinos hold the key to unlocking some of the biggest secrets of the universe. They are born from the most energetic events in the cosmos, from the heart of the sun to the explosions of distant stars. By studying these ghostly particles, we can gain insights into the fundamental laws of physics and the evolution of the universe itself. But how do we study something that is so difficult to detect? Scientists have built massive detectors, buried deep underground or submerged in the depths of the ocean, to capture the faintest whispers of these cosmic messengers. And what they are discovering is revolutionizing our understanding of the universe. Join me as we delve into the fascinating world of neutrinos, exploring their unique properties, their role in the cosmos, and the groundbreaking experiments that are revealing their secrets. Neutrinos are unlike any other particles in the universe. They are incredibly tiny, even by the standards of the subatomic world. In fact, for many years, scientists believed that neutrinos had no mass at all. We now know that they do have mass, but it is so small that it is incredibly difficult to measure. Another unique property of neutrinos is that they have no electric charge. This means that they are not affected by electromagnetic forces, which are responsible for most of the interactions we see in the everyday world. Unlike electrons, which are repelled by negative charges, or protons, which are attracted to negative charges, neutrinos travel through the universe largely unhindered. They pass through planets, stars, and entire galaxies as if they were empty space. Neutrinos interact with matter only through the weak force, which is much weaker than the electromagnetic force. This means that neutrinos rarely interact with matter at all. To give you an idea of just how weakly neutrinos interact, consider this. A light-year-thick wall of lead would stop only about half of the neutrinos passing through it. These ghostly properties make neutrinos incredibly difficult to detect, but they also make them incredibly valuable as cosmic messengers. Because they interact so weakly with matter, neutrinos can travel vast cosmic distances without being absorbed or deflected. They carry information from the most extreme environments in the universe, places that we could never hope to study directly. For decades, physicists believed that neutrinos were massless particles, zipping through the universe at the speed of light. However, in the late 1990s, scientists made a groundbreaking discovery that changed our understanding of these elusive particles. They discovered that neutrinos can change their identities, a phenomenon known as neutrino oscillation. Imagine a particle that starts its journey as an electron neutrino, one of the 3 known types or flavors of neutrinos. As it travels through space, it might oscillate into a muon neutrino, and then back again, or perhaps even transform into a tau neutrino. This constant dance between flavors is what makes neutrino oscillation so fascinating and complex. But neutrino oscillation also revealed something even more profound. It implied that neutrinos must have a small but non-zero mass. According to the laws of physics, only particles with mass can oscillate. The very act of changing flavors requires a tiny amount of mass. This discovery sent shockwaves through the physics community. It challenged the standard model of particle physics, which had long predicted that neutrinos were massless. It also had profound implications for our understanding of the universe, as even a tiny neutrino mass could have a significant impact on the evolution of galaxies and the large-scale structure of the cosmos. Section 4. Whispers from the Cosmos. High-energy neutrinos and their sources. While most neutrinos that reach Earth come from the Sun, scientists have also detected neutrinos from far more distant and energetic sources. These high-energy neutrinos carry information about some of the most extreme environments in the universe, including supernovae, black holes, and active galactic nuclei. One such source is the blazar, a type of active galaxy with a supermassive black hole at its center. Blazars launch powerful jets of radiation and particles into space, and these jets are thought to be responsible for accelerating protons to incredibly high energies. These high-energy protons can then interact with other particles or radiation to produce high-energy neutrinos. In 2017, scientists announced the detection of a high-energy neutrino that originated from a blazar billions of light-years away. This discovery, made by the IceCube Neutrino Observatory in Antarctica, marked a major milestone in neutrino astronomy. It provided the first direct evidence that blazars are sources of high-energy cosmic rays, the most energetic particles in the universe. The detection of high-energy neutrinos from blazars and other cosmic sources has opened a new window into the universe, allowing us to study these extreme environments in a way that was never before possible.